Hi friends, welcome. Today we're going to see how we can optimize container images. What are the best practices? I'm going to list 5 of them, and we're going to go from the use of latest to discuss how to minimize the image itself, the footprint, and reduce risks. And also we're going to see what is the infamous problem of the PID1 with the container images when creating them and how to manage that. So let's start with the use of latest. So one thing I always say, the use of latest should be discouraged at anywhere, especially when building Docker images. Why? Because when you have from image latest, what you're going to do is simply make your build completely uncontrolled because it's not reproducible. Reproducibility is a big topic that we'll probably discuss in another video when talking about container images, but using latest, it's a guarantee that you're going to lose 100% of your reproducibility. Why? Because as soon a new image is released, the new base image that you're using for your image is released, you're going to end up with a different artifact, and that is something that you don't control because someone else that is maintaining your base image can release a new version, and that version may be incompatible with what you have done in your build. So months after your build, you are rebuilding because you're adding new features, something in your image, and you will see that that is broken. And apparently your code change is not supposed to break that image. So it's going to be very hard to debug and figure out what happened. So that's why the best practice number 1 is to pin your Docker base version. So in your Docker file, always remember to use a specific version, and if you can, use the SHA of your image. So because even tags can be redefined, so with the SHA you have 100% guarantee that your image is going to stay the same. So now let's see what's the next one. So one thing, especially if you are coding in Golang and you are containerizing your Golang application, try to use Scratch if possible, because what is Scratch? So Scratch is the base Docker image for excellence. So it's the smallest Docker image that you can use as a base image, and is an empty image. So there is absolutely 0 files in that image. So why is important? Because when you keep your image as small as possible, you have a number of benefits. So you reduce the space occupied by your image. You improve the speed because downloading a smaller image is faster, loading a smaller image is faster, and then you improve security because every single file that you have in your container can be exploited by vulnerabilities, and this is important to keep to reduce the attack surface by having the least amount of files and dependencies inside your Docker image. So these are the reasons why you should try to use Scratch if possible, because Scratch is 0 files. This is obviously not always possible or practical because you may have some subsystems that require more dependencies with the operating system, like libraries that are used by different compilers or different interpreters. So you need to make sure you have the some additional dependencies in your image. So it may become very unpractical to copy everything on the base Scratch image. So if you cannot do that, we can at least try to minimize it, and that's where we go with the best practice number 3. So minimize the image size. So to minimize the image size, there are few things that we can do. For example, in this example, they show a bad Docker file and a good Docker file. On the bad Docker file, we have from Debian 11, so here they pin the version, and then we have a list of commands. So all these commands, run, they are going to create a single layer. So to minimize the amount of layer in Docker, what they are doing is collapsing everything into a single Docker command. So under a single run, you have all this, and this guarantees that you reduce the amount of layers in your Docker file. So this is one way. There are other ways where you can leverage multi-stage builds. A multi-stage build, I can find an example on the Docker page, Docker documentation. So a multi-stage build is a Docker file that contains multiple from commands. So in this example, you can see there is a Maven Tomcat example on the Docker documentation. We have from Maven and then we specify as build, and then we have a number of commands. This is if you know how Java and Maven works, this is packaging our Java application, and then what we do at the end, we do from Tomcat, and then we copy just the Word file that has been created as part of the Maven package into our image, which is now our base image is the last one, so it's Tomcat. So what we're doing here, we're doing copy from build the file, and then we're copying this file directly inside the Tomcat. So any file that has been generated during the build process is automatically removed because it's not part of the final base image, as the final base image is Tomcat. So we are just copying what we have built. So this is quite a nice example. Let's see the other one. There is another one about React. So here we can see that we are doing a similar thing. So we are building our application. This is a web application. So we are executing all our commands. And then at the end, what we are doing, we are copying from build. So this build refers to the name of the image that we used here. And then we are copying the files that we have created in our previous step, and we are copying them into Nginx Alpine. So this is an image that will only expose a website, and there is nothing about the source code, only the output that has been generated as the build process. So there is another thing that I really like about this from command. I'm going to show you. So if you look at this file, I have this file, and I'm creating from scratch in this case, and then the thing I wanted to show is using copy from by using directly an image that we can reference here. So here what I'm doing is I'm copying directly from the Terraform image, the Terraform executable. This is a standalone executable that doesn't have any dependency. So we can copy this, and the other thing we can do is copying the certificate. So this is probably something you have to do every time you create an image from scratch. So copying the CA certificate, so every TLS connection can be validated against the CA certificates, and then at that point we can run the Terraform command. So if we want to execute this, I can show you. We can docker. We can docker build. We can run docker build for this Docker file, and this should build the image by copying everything from the other things. So now what we want to do, we can execute this and see if that actually works. So this should execute the Terraform command. And as you can see, we are able to execute the command. So this is just to show you how to use the -- from. So another best practice for container images, probably you have guessed that by this time, is to keep the images with a single responsibility. What do we mean with single responsibility? Is that we want to run a single process inside our container image instead of multiple processes. There are a number of reasons because we want to do that, but by design, Docker is supposed to run a single process. So, and this one leads to the last example, the last best practice, which is the PID1 problem. So what is the PID1 problem? There is a brilliant blog post that I'm going to link down in the description that is going to do a better job that I can do in this video, but I'll try my best to explain what is the PID1 problem. So essentially, the Linux operating system runs the PID1 process, which is the first process when you start your operating system, in a different way compared to the other processes. It does that because that process is the one that is going to create all the other processes, all the child processes, and has also one important objective, which is the one of cleaning up the processes when they terminate. So essentially, the PID1 is supposed to call a system call that is the wait system call on the processes that have been terminated. So I'm going to read from the actual system call documentation. So a child that terminates but has not been waited for becomes a zombie. The kernel maintains a minimal set of information about the zombie process, speed, termination status, resource usage information in order to allow the parent to later perform a wait to obtain information about the child. As long as a zombie is not removed from the system via a wait, it will consume a slot in the kernel process table, and if this table fills, it will not be possible to create further processes. But this is related to operating system, and we know that containers are not running operating systems. But the important thing is that a container, when we launch a container, that creates the process as a PID1. So that PID1 is expected to operate as we do with the operating system. So that means we have to manage that by ourselves. There are different ways to overcome this issue. So Docker included the --init command that can be executed when we launch the container. And now also in Kubernetes, we can enable a flag, which is shared process namespace, that allows us to manage this aspect automatically. But a good practice is to keep a small init system inside our containers that manage all the system calls and the sig terminations automatically. So for example, you can use Tiny, which is a very small init system that you can use with container images. So what you can do, you can, whatever command you can execute, you can prepend Tiny in front of it. So you install Tiny obviously, and then you can prepend this command. Will wire all the signals and make sure your container manages them properly. So, and you can find the link in the description about Tiny, and this is it. Let me know if you have questions. Don't forget to subscribe, and see you in the next one. Bye bye.